Okay. Okay. Good afternoon, everyone. Today we have two members of our group to present. The first is Mr. Jamilu Yahaya. Are you ready?
Yes, I'm ready.
Okay, you can start now.
Okay, good afternoon, everyone. Today, I'm going to present an important topic. The title of my presentation is A Note on the Convergence Properties of YL. That is, in short, we call it WYL, Conjugate Gradient Method for Solving Vector Optimization Problem. My name is Jamil Yahya, and this work is supervised under the supervision of Dr. KMUTT. This is the outline of my presentation. In vector optimization, one investigates optimal elements such as minimal, strongly minimal, properly minimal, or weakly minimal elements of a non-empty subset of a partially ordered linear space. So vector optimization problems are a significant extension of multi-objective optimization problems. Problems of this type can be found not only in mathematics, but also in engineering and economics. So most of the real world problems involve simultaneous optimization of several objective functions. So these objective functions are measured in different units and are often competing and conflicting. Vector optimization having such conflicting objective functions give rise to a set of optimal solutions instead of one optimal solution, because no solution can be considered to be better than any other with respect to all objectives. So these optimal solutions are known as Pareto optimal solutions. So next we are going to look at a graph of how we represent the solution of vector optimization problem. So looking at this graph, figure 1, we said Pareto optimal solution. So if you look at, we have two objective functions here. We have the f1 of x and the f2 of x. So we have a curve here, this green curve with a line. The line is called the Pareto front, while the green dot on the line are called the non-dominated particle or non-dominated solution, because I extracted this from a problem that involved a particle. So that is why it's called non-dominated particle. But in this case, you just consider it as non-dominated solution. So the other dot up there above the curve is what we call dominated particle. So in order to do this in a better way, let's look at the next motivation. So if you look at this, minimizing radiation on tumors while minimizing it on the surrounding, maximizing radiation on the tumors while minimizing it on the surrounding healthy tissues. It is just like a kind of multi-objective optimization problem, or in general vector optimization problem with two objectives. We are trying to maximize one, that is the radiation on tumors, while trying to minimize the radiation on the healthy tissue. So these are two, we have two objective functions there, with competing and conflicting interest. So this particular example of Pareto optimal solution, we are going to consider 9 types of air tickets with different time and cost. So in this case, in this air ticket type, our objective functions, the first objective functions is time and the second one is cost. The target here is to minimize the time and to minimize the cost. Maybe you want to travel and you have 9 options of air tickets, but you want a ticket that that is less in price, while the time taken to reach your destination is also less compared to others. So in this particular scenario, if you look at ticket A, that is ticket type A, we have ticket type A to I. So ticket type A, the time taken to reach your destination is just 2 hours, but the cost of the ticket is 7.5 in baht. So if you look at around all the cost from A to I, 7.5 is the highest. and there are only two tickets that has the cost 7.5, which is the A and C. But if you compare A and C, you will notice that the time taken to reach the destination for air ticket A is less compared to air ticket C. So in this case, we can now say that A dominates C. That is, A is more important than C. If you compare also B and C, you will notice that B dominates C because the time taken to reach destination for B is the same thing as C. But the cost, when it comes to the cost, B is more important than C. So therefore, we can now say that A and B dominate C. Again, if you look at the case of D, you will notice that D has high cost compared to A and B and C also. But the cost of air ticket is less than all other ones. All other is less than A, B, and C. So therefore, in this case, if you compare D with E, with G, H, and I, you will notice that we can now say that in this case that A dominates C, B dominates C, E, G, H, I in terms of what? In terms of cost, time at some instances. Also, if you look at D, you will notice that D dominates E, G, H, I. If you look at it in terms of what? In terms of cost, sorry, in terms of time, because the time taken for D is the same thing as that of E, but when it comes to the cost, you will see that D is better than the E. But in terms of time, D is better than all other ones, E, F, G, H, I. So therefore, in this case, we now said that A, B, D, and F form a non-dominated set. That is, if you look at this graph that we left here, A, B, D are the ones on this green line, are the green circle on the green line, while the E, F, G, H, and C, sorry, C, E, G, H, I are the ones in circle green. That is what we call dominated solution, because the other ones are beta. So if we are to plot the graph of that particular scenario, it will be just like A, B, D. That is A, B, D, and F will be on the green line here. So this is one of the motivation of studying vector optimization problem. Hence, in conclusion, we can now say that this A, B, D, and F form a Pareto optimal front, which sometimes we call it non-dominated front, and these are called the Pareto optimal solution. So if you look at it, in just a case of 9 objective functions, we end up having a solution of about how many? That is about minimum of 1, 2, 3, 4. That is 4 minimum. So therefore, this shows that in the case of vector optimization, you hardly whenever you are dealing with vector optimization, you are dealing with a problem that involves several objective functions, and the solution may not be a single solution. So in this presentation, we'll take you through the following unconstrained optimization problems: the unconstrained single objective optimization and the unconstrained vector optimization problem. It is assumed that the audience are familiar with the item 1, that is the unconstrained single objective optimization. So it is skipped for due to time factor. So minimization problem, vector minimization problems deals with problem 1, that is minimize with respect to k, f of x, where x is a decision variable in Rn, and f is from Rn to Rm, is continuously differentiable function, and k is a source of Rm, which is the image, subset of the image, is closed, convex, and pointed cone with non-empty interior. So the partial order in Rm is represented as this, that is partial K, induced, while the interior is represented as this this particular one, that is the interior, while this one is for the just direct partial order. So this is when we said that U is partially ordered with respect to K of V, this implies that V minus U is in K, respectively in the interior also. So the Pareto optimality or Pareto efficiency is a point X bar in Rn, such that there exists no order X in Rn, with f of X less than or equals to that, with f of X partially less than f of X bar, and f of X is not equal to f of X bar. So from this Pareto optimality definition, you will notice that there is no way you can say A is better than B here, or A is less than B, or B is less than E. So that is why we arrive at the solution of this particular problem, because whenever you compare the two, you will notice that one is either less than this, the other one is less, so you cannot say exactly that this is less than or equal to this one. So for more, in other words, this is a way of finding unconstant minimizers for F with respect to the partial order induced by K. So for more information on this topic, one can check reference 1, 2, and 3. So these are some basic definitions of convex set which are familiar with, which we are all familiar with. The cone, convex cone, and the pointed cone, convex hole, which all I have explained in the previous presentation. So now we are going to look at another simple and very straightforward example, although it's not actually straightforward, but it is very important. The minimal element. This definition is very important because we have different types of solutions actually. When we said Pareto optimal solution, we mean either minimal, weakly minimal, strongly minimal, or properly minimal, which I have explained earlier. So it is important to look at this. Okay, how do we find a solution when we are in R2? Because since our function is a map from Rn to Rn, so let's just take a simple case, R2 to R2, for example. So we now take this example. This particular figure is extracted from Jan 2011, Vector Optimization Theory and Applications. So if you look at it, this graph, M is defined in such a way that it is this yellow color you are seeing is what we call M, while R2 plus is 0, 2 to 0, 2 on the X and Y axis. So clearly, if you look at this thing, now if you want to find strongly minimal, from the definition of strongly minimal here, it says that V is list of any element in K. That is what we call strongly element. For all element in M, V in M, so V bar is less than or equal to that with respect to the partial order K. So if you look at it, which element in this particular set, which element is the list of all element is 0. 0 is the least element in this particular set. But is 0 in M? 0 is not in M. And so therefore the strongly minimal is actually empty. So before I explain the other ones, I would like to tell you that strongly minimal is one of the most, according to the theoretical aspect of vector optimization, it's one of the most important solution concept. But for just a simple example of R2, we cannot get the strongly minimal solution. So therefore, this shows that theoretically is important, but in reality is hardly for one to get strongly minimal. So the next thing we are going to look at is the minimal itself. So when we set a minimal, this is the definition of minimal. This bullet, second bullet, is the definition of minimal. So if you look at the graph, you will notice that minimal element is the element is on this particular line, just like a Pareto front. If you look at it, you see this star green on one and on the Y axis and star green on X axis. So is the interval between where we have the minimal elements. That is including 1 and 1 there on the y and x axis. That's the minimal element from the definition. Also, if you look at it, you will notice that minimal elements are more important in reality than the strongly minimal here. Then the next thing we are going to look at is the properly minimal. The properly minimal is the set between the star between 1 and 1, that is from here to here, but 1 and 1 are not included. So we said it's between 1 and 1, 1 and 1 not inclusive. So therefore, in this case, you will notice that strongly minimal is less because it is empty, followed by what? Followed by minimal, followed by properly minimal, which is less, is between 1 and 1, but open, while the minimal is between 1 and 1, closed. So now, the next thing we're going to look at is the weakly minimal. The weakly minimal elements is from 2 on the y-axis to 2 on the x-axis. It takes all the Pareto non-dominated solution line. So it takes all the Pareto front line from 2 to 2. This shows that weakly minimal is the largest of all set of solution. So in order, the one that we are very sure of is in most cases is the one we actually go for. If you look at it, the properly minimal, the minimal are in most cases are less. So whenever we're looking for solution, in most cases we'll go for weakly minimal. So now we are going to look at the functions, the definition of functions that lead to the derivation of some beta case in these settings. So this is the definition of zeta from Rn to Rm, which is defined by equation 2. And this definition 3 is also very important. So this particular definition 4 and definition 5 plays an important role in this concept. So the next thing that is actually very important also is equation 6, which is the definition of sufficient descent. This definition is extended to vector settings by Lucambia and Peros in their paper in 2018. So the next important thing is we know that even though exact line search are not really applicable sometimes in reality, but they are important. It is important to extend it to this setting. So they also extend the exact line search, which is given by equation 7. So another set of important conditions, which are the warp conditions, have also been extended to these settings by Lucambia and Peros in their book, in their paper 20, which was published in Siam Journal of Optimization on Optimization 2018. So this equation 9 and 10 give the standard warp condition, while equation 11 and 12 give the strong warp condition. So now we are going to give the convergence analysis. So before the convergence analysis, there are some 2 important assumptions that we normally make when we are dealing with, when we want to prove the convergence of our algorithms or the algorithm in these settings. This is the algorithm actually. This algorithm was first given by Lucambia and Peros. So in this case, we need to understand what is this YWL conjugate gradient method. This WYL was actually coined as it was shortened to WYL because it is the name of the authors, Wei Yao Liu, that published a new algorithms or proposed a new algorithm in 2006 and named it Wei Yao Liu. This algorithm actually is just like a kind of PRP type, which they introduced this particular norm of the gradient all over norm of the previous gradient. That is gradient at the current iterate and all over norm of the gradient at the previous iterate. at the numerator of the PRP. So they call it Weiyao-Liu. So this beta K is actually plays an important role in the scalar optimization because it shows robustness and efficiency in terms of convergence. But one thing that I want us to understand here is that the concept of PRP that was proposed by Lucambio, Peros, and Prudenti in 2018, they were able to establish the result of Gilbert and Lesser of 1992, which they were able to show that PRP algorithms involving PRP method does not require sufficient descent for its convergence. So in this case, you are able to establish the same result here. They prove the convergence of the PRP method without the sufficient descent condition. They only just make an assumption of descent property. So here, we also establish the convergence of Weiyao-Liu conjugate gradient method without the sufficient descent condition. Using with strong Wolff condition. So this theorem actually gives us the convergence of PRP, HS, and LS. The theorem says that when you have beta K positive for all K, and DK is sufficient descent, while in the case of PRP, DK is descent, satisfied descent condition, and alpha satisfied the strong Wolff condition for all K, then and property star holds. This property star was first given by Gilbert and Lesser. So I think in the last presentation I gave this property star, but because of the time factor, I actually extracted it out here. So if you have these four properties, then you have the global convergence of the PRP, HS, or LS methods. So this is the main theorem of this particular Weiyao-Liu conjugate gradient method for vector settings. Suppose that assumptions A and B hold, then consider algorithm 1 with beta K of Weiyao-Liu conjugate gradient method being positive for all K, such that the sequence SK-DK is generated. So if DK is K descent direction of F at SK and alpha K satisfy the strong Wolff condition 12, then we have the strong convergence. We proved this successfully without having so much headache and without the sufficient descent condition, only assumption of the K descent direction. So we establish in this section, we give the numerical experiment to verify the effectiveness of the proposed scheme. Our numerical experiment indicate that the Weiyao-Liu considered here outperforms the PRP plus method studied in 3. That is studied in the Lucambio Peros with the strong Wolff conditions. And it is known that the PRP plus outperforms the method given by the Lucambio Peros and Prudenti in their paper in 2018. They gave 5 different parameters: the PRP plus, HS plus, FR, CD, and DY. But PRP outperforms all other ones. But in our own case here, we compare our result with the PRP plus and discover that our result outperforms the PRP. So look at below is the performance profile of the WYL and PRP plus considering 100 or 200 starting points for the test problems considered. So we considered about 30 test problems, which starting points. The starting point were actually randomly selected by the computer itself. So this is the performance profile with respect to the iterations. So if you look at it, you can see that the WYL performs better than the PRP and its efficiency. While in terms of the functions evaluations, again, the WYL also performs better. In terms of gradient evaluations, the WYL also performs better. CPU, time. So when it comes to CPU time, this also shows that WYL is effective and robust. So concluding remark, in this talk, we present a WYL conjugate gradient method for vector optimization, for solving vector optimization problem. The fact that PRP-CG algorithms do not require sufficient descent to prove its convergence has been extended and justified to the WYL-CG algorithm. Furthermore, Lecambia-Perez and Prudente-3 showed that the PRP plus and HS algorithms are robust and efficient. But in this work, we give a more efficient and robust method compared to the PRP plus. This method shows its efficiency and robustness in terms of number of iterations, functions, and gradient evaluations, and finally the CPU time. These are some of the references. Thank you very much for your time.
Thank you, Mr. Jamilu Yahaya. Anyone has any question?
Okay, Doctor.
Okay.
Very nice presentation, Dr. Jamilu. How are you?
Fine, thank you.
Great. I'm just wondering if you can kind of like highlight or maybe talk again about the algorithm that you propose. Maybe a bit more explanation about it will be okay.
Okay. As I have explained earlier, okay, where specifically do you want me to explain in the algorithm? Is it everything from the beginning to the end, or what?
Yeah, just like the kind of initialization you have. We say that you have starting point and some bunch of parameters which we don't know what they are. Can you explain a bit more about those? Maybe the initialization only.
Okay. Actually, the initialization actually uses because the numerical experiment was carried out in Fortran, so we use what we call seed. Seed actually takes a kind of random starting point. So the reason why we said in the explanation that we use this starting point, we take 200. Sometimes we take an interval, that is, for example, A from A to be equals to maybe minus 100 and B to be equals to 100. So the X naught, which is the starting point, is defined to be equals to A plus, beside, for example, B, A minus B times the seed. That is the random value, the random value in the numerical experiment. So this is how it has been designed in the numerical experiment.
Okay, thank you very much. This is a wonderful explanation. Thank you very much for highlighting or explaining what you have explained again. Thank you very much.
Thank you very much. Can you hear me?
Yes, I can hear you.
Please let me quickly point out some typos at step 1 of your algorithm. Can you check it through?
Yes.
Okay.
Yes, I have seen the arrow. Actually, it is WSK and V of SK.
Yes.
Also, here is if B of SK is actually an oversight while trying to. Thank you very much.
Okay. I would like to know why do you think we should study this kind of algorithms, considering a bunch of algorithms existed in history?
Yeah, that is why actually in the beginning I gave a motivation for studying this particular concept. I have explained, I think I took time to explain in details the importance of this concept. For example, now, as I have give.
But let me say again, I'm not talking about the concept in general. I'm talking about the algorithm. I say we have a bunch of algorithms.
Okay.
Why should we be interested in this your proposed algorithm?
Yeah, in most cases, actually, algorithms are studied when they are robust and efficient. So if you compare my algorithms or our algorithms with the PRP as I've explained earlier, it is robust and efficient compared to the PRP plus. And so far, what we have up to, as to the best of my knowledge, PRP plus in these settings is PRP plus algorithm is the best in this setting so far. So now that we brought a new algorithm which is robust and more effective than the PRP, I think the algorithm is important to be studied.
Thank you very much for the explanation. And I would also suggest probably to look into these kind of parameters from geometric point of view, because I realized the genesis of the first considered parameters actually arise from the geometry, where people come to realize that, of course, if we make certain modification, then it will give a better performance based on the studied problem. However, then some beta parameters may well behave depending on the problem considered. Well, if you change the problem, then the beta also may not behave properly. And so now consider the geometry of both the problem and that of the beta parameter. I believe that one may have some reasonable discovery. Just starting from the ingredient setting, so
The network is cracking. I can't hear you.
Okay. Oh, sorry. I mean, if we can look at it from the geometric point of view,
Yeah.
we will see innovation from the ingredient setting optimization concept. That is my suggestion to you. Thank you.
Okay, thank you very much. Thank you very much. Any other question or suggestion?
Okay, if no any question, thank you, Mr. Jamilu Yahya.
Okay, thank you very much for giving me this opportunity to present some part of my work.
Okay, and the next
Hello, madam.
and the next person is Mr. Papap. Are you ready?
Ready.
Okay,
ready.
you can start now.
Okay. Good afternoon. My name is Papap Namsap. Today, I will talk about fixed point theory for digital contaction. Sorry, can you see my screen?
Yes.
Okay, thank you. Okay, we will the content for the today have 4 parts. The first is digital metric space. What is digital metric space? And second is Rabana fixed point theory for digital image. And third is digital contact map. It's another type of contact map. And the last is application for the paper. The first is digital metric space. Digital image is a subset of the set power n. When the set power n is electric point in the dimension Euclidean space, And digital image consists in X and row, when the row is represent about adjacent relation of the member of X. So we will talk about adjacent. We will say A and B are KL adjacent if they are at most L index I, such as absolute of AI might not be equal to 1. At most L index is mean you can greater than L index, but don't get her. And another pair of AJ and BJ must be equal. I think definition is like here, so I have some example. A and B in sets or in integer number are two adjacent if absolute of A may not be is equal to 1. And the two adjacent because A have a 2 point B dash are two adjacent. And A and B are X adjacent if they are distinct and differ at most one in earned coordinates. And for adjacent if they are X adjacent and differ in exactly one coordinate. And it a illustration for adjacent of Z and Z square. In the picture A, it's a two adjacent. You can see P adjacent to 2 point, and in 4 adjacent, P adjacent to 4 point, and X adjacent is also adjacent to X point. So in subproperty or cubic, A and B are 28 adjacent if they are distinct and differ by m more 1 in earned coordinate, and 18 adjacent if they are 28 adjacent and differ m more 2. And the last A and B are 6 adjacent if they are 18 adjacent and differ in exactly 1. You can see this. This is differ at more 1 in 3 coordinate at more 3. And this is differ at more 2 coordinate. And there is 1 coordinate. It's like you can step it. Subproperty it have 3 steps. Subpower 2 and have 2 steps. Okay, and this is illustration. This is X adjacent. This have a X box adjacent to the middle or the center. And 18 adjacent and 26 adjacent. Okay. Next we'll talk about neighbors. Neighbor is a vertex that adjacent to the vertex. It's like a neighbor of A is a vertex that adjacent to A in low adjacent. A neighborhood, low neighborhood of A is a set of the vertex that's vertex or point that is low adjacent to A. And digital interval between P and Q is all integer between P and Q, and it can equal to P and Q. And it's so, and the space is low connected if every pair UV in X that have a set U0 to UR that U0 equal to U and V equal to UR, and UI and UI plus 1 are low neighborhoods, or they are adjacent in low adjacent for I equal to 1 to minus 1 is like a pass in actually. Okay. The function on digital image is have a continuous as function in another metric space. But if it continues if for every low zero subset of U. For every low zero connected subset U of X, and FU is a low one connected subset of Y. We will say this F is low zero and low one continuous. We have a low zero and low one because for different space we can use different relation of adjacent. Inside X we can use low zero, and Y we can use low one. X and Y can dimension is not same, and also adjacent relation it cannot same. And F is low one, low zero, low one continuous for even only for every pair of x0 and x1 of x that's low zero adjacent. Either f x0 equal to fx1 or fx0 and fx1 are adjacent in low one. Okay, the next part, I think some definition are well known. Like a Cauchy sequence, a sequence again. The Cauchy sequence is for all epsilon greater than 0. The distance between xn and xm is less than epsilon for every n and m greater than some alpha n, and convergent to p. If for all epsilon greater than 0, the time between xn and p is less than epsilon for all n greater than alpha, like this. And our complete digital matrix space. Digital matrix space is complete digital matrix space if for any Cauchy sequence xn have to convergent to some point in this space, and like continuous if the TP is equal to limits of Tx when equal to P on the right hand side. Okay, and the contact mapping. T is called digital contact map. If the distance between Tx and Ty is less than or equal to alpha the xy, when alpha is in the interval 0 to 1, it can be 1 and it can be 0. Okay. And there is some proposition. Every digital contact map is digital continuous. And this, I think, is some well-known binary contact principle. If T is a digital contact map, T has a unique fixed point. Okay, next we will talk about digital contact map. This is another type of contact map, contraction map. Like can digital contact map. T is a canal digital contact map is distance between Tx and Ty is less than or equal to lambda multiplied by dxt, dx and tx plus dy and ty. When lambda is in this interval 0 to 1/2, you have to say this. It not lambda from 0 to 1, not. Okay, next we will talk about property of the contraction. If K is a canal digital contact map, T has a unique fixed point, but we can make a generalization of canal contact principle. We can make some function epsilon that sends some value from the code interval 0 to u to 0 to u 0 to u over 2. When u is a round real number and the epsilon a is defined by epsilon A less than A over 2 if A is positive. But if A is 0, can be another. And T will satisfy like this. Distance between T x1 and x2 is less than or equal to epsilon multiplied by the sum of dx1 and tx1 and dx2 and tx2. It's like a kind of contact principle, contact map, but we change the constant to a function. And moreover, T had a unique fixed point by contact map. And we have T and X convergent to C. Every X in this space and C is a fixed point. Okay. And we will say T is some Phillips digital contact map if T satisfies like this. T is less than or equal to lambda max of this set, and in this case, lambda is like a contact map. Lambda is in this interval 0 to 1. Okay. But in this contraction type, if T is satisfied by some Phillips digital contact map, T had a unique fixed point, like in the next type, but the next type is like a general than the previous slide. The Rhodes digital contact map is similarly to the previous slide, but if you see the term, it don't have a over 2. And if you see the lambda is 0 to 1 is same, but it's general than the Phillips digital contact map because it's have a over 2, but don't have in the case. Okay. And the proposition for this contact mapping. Loaded contact principle says let T be a loaded digital contact map. Then T had a unique fixed point. Okay, this is end of the result for the paper, but we will talk about the application. The application is Sierpinski carpet. I think the name some people don't see this, but I have some picture to explain you. The application is like you have one picture, one big picture, like a big triangle. You have to make a small and small and small. You add a detail in the triangle. The first, we have a triangle, right? We consider the triangle and make a T copy of it in exactly half of its dimension. It means a half size in dimension of the picture, is like this. And they said the one of the copy paste on the top vertex, and the second paste on the left, and the right paste on the right. And we consider the new triangle, and we do it again until this again and again. So it's like a loop. After we do a loop for a long time, we can get a lot of detail. Okay, we will see a picture. Like this, we have a triangle. After that, we generate this one time. We copy the picture in iteration 1 and put in half dimension. It's half size to pair in this, and this, and this. After that, we use this is a triangle that we consider and do it again to get this. And do it again to get this. And you can say this, the number of triangle is will be increase and increase and increase, right? So if you do it in a pixel of the picture, you can add some detail to it. It can have a lot of detail. Or you can change the polygon to smooth. But the concept of Sopensky is not for only a triangle. We can use in a regular polygon or another thing. You can use in a 3D picture or 4D. You can see more in this thing. And this is another example. This is a picture in the first generation. After that, we generate this. You can see this is the first generation. After that, generate this again. And you can see this as second generation. And generate. You can use the concept to add some more detail in every shape. Okay. If you want to see another example, you can see in this link. And I have to thankful for the website because I use the picture from the website. And paper that we talk about is in this seminar. It's the paper, and the paper is from the journal. Okay. And this is another reference if you want to learn more about digital topology and the function. Okay, thank you.
Anyone has any question or suggestion to him? Okay, if no any question, please turn on camera for taking picture.
Hello? Hello?
Hello.
Sorry for not preparing well, but I can present something just for a few moments, if you allow me.
น้องหมีให้เขาพิเศษวันไหนอ่ะน้องหมี
ค่ะว่าไงนะคะ
ให้เขาพิเศษวันไหนคะ
ก็เลือกวันมาให้เขาเลือกวันมาได้เลยค่ะ วันที่เหลือยกเว้นวันพุธที่จะถึงนี้ค่ะ
Okay, you can choose the date for present is not this Wednesday. Another you can choose the date for present Monday or Wednesday, but the date is from the next week.
Okay. Possible.
Everyone, please open camera for taking picture.
ขออนุญาตไม่เปิดนะคะ สภาพไม่ได้เลย